is a model of a neuron. My kids think this model looks creepy, but it's kind of what we could visualize a neuron looking like. Now, I want to show you some of the parts here that we kind of the terms we throw out. So this right here, if anybody has taken any science, is going to know, is a nucleus. And a nucleus is where the neuron fires electricity to start the electrical chemical response. This is our axon. And our axon is the long arm of a neuron that carries the electricity and chemicals to communicate with another neuron. Some axons can be up to 3 feet long. It's important to know the difference because this part, the bigger, mushier looking section, that's our myelin. I knew I would misspell. That's our myelin. All right. I'm notorious for being a terrible speller here. But so myelination is when we recall facts and experiences from our memory. The axon lays down this fatty sheath called myelin, and it's similar to like an electrical cord's insulation. The more memory that's retrieved and stored, the stronger this myelination gets. Moving right along. These guys right up here, these like spine-like projections, this is I'm double checking that spelling. These are our dendrites, right? And our dendrites, I'm probably pronouncing it wrong. I'm known for that too. These are finger-like projections on the neuron. This is how the axon communicates with dendrites. When we learn something, we grow dendrites. This goes with our axons. This is our axon terminal. What is key here is, do you see where the dendrites are touching the axon terminal? Well, this little process is what is called our synapse. And synapses are what the chemicals travel down the axon to the terminal. So from here to here. And they jump across a space called the synapse. And they lock on to the dendrite receptors. Now what is interesting is that a brain-derived neurotrophic factor, otherwise known as BDNF, that coats the synapses so that the path for the neurons are able to communicate to one another. You cannot get BDNF without adequate physical movement. I don't know if you're catching what all of this is and how it's giving us an optimal environment for learning, but it's really spectacular. What's interesting is that from about the ages of 12 to 25, our children's brains are remyelinating, or they're going to soon start somewhere in there. The difficulty with this age is that their hemispheres are not communicating the way that they will after this myelation occurs. This process of myelation makes it easier to focus in on a task and learn something new quickly. However, if you are asking one learning style during this remyelation period, if you're asking this 1 week learning style to receive information that's unfamiliar to them, it's going to take time to adjust, which is why we've taught you about wait time and learning styles. And now we want to teach you about how to increase this optimal learning environment.